Okay, here we are for Advent of Code 2021, day 20. We are getting down to the last 5 or 6 problems. Today we're going to be doing it in Rust. Yesterday's problem was quite challenging. We were eventually able to get it after a couple hours when I looked on the Reddit solution thread for yesterday's problem. I think a lot of people had issues with it, and a lot of people also came up with solutions that didn't perform very well, and that was certainly true of my solution. So if there's time, or if I'm feeling like it after today's problem, I might roll back also to day 19 to see if I can't add some optimizations to it to make it run a little bit more in line with what I'm used to for these problems, which is basically to say that when you run the program, it basically solves it like kind of like instantaneously, at least from the perspective of a human timescale. I would love to go back. It's a little bit stuck in my craw. I actually, truth be told, took some time to try to optimize it further, and I really didn't stumble upon anything that was like a silver bullet. I got it down to about a 10-second runtime, and I got it doing like incorrect answers at a 6-second runtime. So who knows whether that was, pulling on the right thread or not. Anyways, before we get into that, let's just go ahead and try to take care of today's problems, because who knows, today's problems might just be even harder than yesterday's. So let's take a look. All right, we are on day 20, the trench map. With the scanners fully deployed, you turn their attention to mapping the ocean floor of the trench. When you get back the image from the scanners, it seems to be just random noise. Perhaps you can combine an image enhancement algorithm and the input image, which is your puzzle input, to clean it up a little. For example, there's this giant field of hash marks and periods, plus a little thing down here. The first section is the image enhancement algorithm. It is normally given on a single line, but it has been wrapped to multiple lines in this example for legibility. The second section is the input image, a two-dimensional grid of light pixels, hash mark or octothorpe, and dark pixels, which is the period. The image enhancement algorithm describes how to enhance an image by simultaneously converting all pixels in the input image to an output image. Each pixel of the output image is determined by looking at a 3x3 square of pixels centered on the corresponding input image pixel. So, to determine the value of the pixel at 510 in the output image, 9 pixels from the input image need to be considered: 49, 410, 411, 59, 510, 511, 69, 610, and 611. These 9 pixels are combined into a single binary number that is used as an index in the image enhancement algorithm string. For example, to determine the output pixel that corresponds to the very middle of the input image, the 9 pixels marked by ... would need to be considered. Marked by square brackets. Starting from the top left and reading from across each row, these pixels are ... then hash ... then hash . Combining these forms ... hash ... hash ... I can't really read that out loud, but I think you get what I'm saying. By turning dark pixels, which are dots, into zeros and light pixels hash into 1, the binary number 001010 can be formed, which is 34 in decimal. The image enhancement algorithm string is exactly 512 characters long, enough to match every possible 9-bit binary number. The first few characters of the string number starting from 0 are as follows. In the middle of this first group of characters, the character at index 34 can be found, a hash. So the output pixel in the center of the output image should be hash, a light pixel. This process can be repeated to calculate every pixel of the output image. Through advances in imaging technology, the images being operated on here are infinite in size. Every pixel of the infinite output image needs to be calculated exactly based on the relevant pixels of the input image. The small input image you have is only a small region of the actual infinite input image. The rest of the input image consists of dark pixels ... For the purposes of this example, to save space, only a portion of the infinite-sized input and output images will be shown. The starting input image, therefore, looks something like this, with more dark pixels ... extending everywhere in the direction not shown here. By applying the image enhancement algorithm to every pixel simultaneously, the following output image can be obtained. Through further advances in imaging technology, the above output image can also be used as an input image. This allows it to be enhanced a second time. Truly incredible. Now the small details are really starting to come through. After enhancing the original input image twice, 35 pixels are lit. Starting with the original input image and apply the image enhancement algorithm twice, being careful to account for the infinite size of the images, how many pixels are lit in the resulting image. Okay, so this is actually a pretty cool problem. It actually sort of reminds me of doing image processing, or I think more relevant to what this stream is normally about in game development. It's almost like doing a kind of like fragment shader or pixel shader, one that actually sort of like looks at neighboring pixels of the current pixel you're trying to process. So you would do something like this if you're trying to blur. You might be doing something like this if you're trying to maybe do edge detection or that kind of thing. You're essentially looking at the neighbors of a pre-image in order to determine their influence on the output color of a particular pixel. So the kind of like input, the first part of the input, which is what they're calling the image enhancement algorithm, is almost like a texture map, right? You're like kind of like reading one texture and calculating some sort of summary value, and then using this as a lookup table to come up with the actual value that you want. Okay, one thing I'm curious about is the infinite nature of this, right? If you're interested in, let's say, this is your input image, but you're interested in the pixels that are immediately around this, I'm guessing that we assume that the input image is just extended with dark pixels or values of 0. And this first part of the problem is just asking us to process this this algorithm twice. And doing it twice is not too bad because we can essentially like encase the input image in a large field of dots, and then just run it twice. If I had to predict what the second part of this problem is going to do, I'm guessing that they're going to ask us to run this like 1,000 times. In which case, it might start to get untenable to to basically maintain a full grid that looks like this. So we have to think a little bit about how we want to represent our input images and our output images. The thing that immediately comes to mind is basically just, rather than storing a grid, we could create a set that contains variables. A set that can just contains coordinates of the locations that are lit up, and that theoretically would save a lot of space. So that's actually, I think, a reasonable representation to start with. The second question that comes to mind that I don't have an immediate answer to, but I think we can figure it out relatively easily, is if you're trying to emit an output image, where do you start, right? Like, you need to know, because the image is like infinitely sized, you need to know when you start looking for lit pixels. And I think what that is going to end up meaning is that you want to start, well, if you started, let's say our input image is here, right? This is the input image buffered by a bunch of dark pixels. If you started processing your output image at this coordinate that I've highlighted here, it's going to end up being the binary value 0. And as long as I believe the input algorithm, this sort of lookup table, is always going to start with a dot on 0. Oh, in this case, it doesn't, which is really interesting. And the reason why I am curious about that is that if you have 0, then doesn't that mean that every pixel is going to be lit up? Or is it that if you add up, well, what is this? 0, 0, 0, 0, 0, 0, 0, 0, 0. You're going to have 0 all around. That means that this is going to be lit up. So doesn't that mean everything is going to be lit up infinitely? Have I misread this? The small input image you have is only a small region of the actual infinite image. The rest of the input image consists of dark pixels. Right. And a dark pixel counts as 0, right? Pixels dot into 0 and light pixels hash into 1. And the binary number... So the binary number of this 9 element, let's call it a kernel, right? This 9 element kernel. The binary number is 0. And in the lookup table, entry 0 is lit. So what I don't understand is if the output image is infinite, it seems like we just have an infinite number of lit pixels. However, we are running it twice, right? And if we run it twice, that means that a 3 by 3 empty space will basically turn into a 3 by 3 lit space, and that's going to be mapping to the number 511, which is blank. So maybe that's the trick, is that we need to figure out how to handle the mapping, assuming that we've run it twice in a row. Otherwise, if we just run it once, we're going to have an infinite number of lit pixels. Wow, we've already gotten a little bit of a juicy problem. This is kind of a slide tackle of a problem because their example does not actually accommodate the input that I'm getting here. Like, I can't just run their algorithm trivially by saying, okay, I'm going to run one image enhancement and then run a second one. Because if I run the first step, the 0th element of this input will basically give me an infinite field of active pixels, right? So maybe what we can do is actually reverse the sense of on and off. And we'll do that in a way that actually gives us an advantage. Maybe that's what we can do. Is that, like, I talked before about our representation just being a hash, like a set of active coordinates. We get to define what is active and what isn't active. Like, we could just arbitrarily flip hashes and dots if we wanted to. And maybe that's a more effective way of handling this. So I guess what I'm saying is we could just flip this input algorithm so that dots mean hashes and hashes mean dots. And I think that doesn't matter as long as we flip it in the input image as well, right? Okay. So we start with the input image. Again, the question is, like, where do we start doing our, like, if we want to progress from one step to the next step, where do we begin, given that the size of the input is infinite? This is already quite the thinker. Well, we know that when we run one step over this using our input, we're going to have like an infinite field of hashes. Up until when? Up until we actually start touching this hash mark, right? And the first time we do that is this 3x3 kernel here. And then the last time we'll run up against that is when we touch this hash mark here. Let me actually copy this in there because I can actually select columns in my text editor. So this kernel here is basically the first one we need to care about. Let's see if I can do this. Yeah, so that kernel there is the first one that we want to care about. And then the last one that we care about is right here. And when I say we care about it, what we really are talking about is we care about like basically the last kernel that contains something other than the infinite digit. And the infinite digit is going to vary. It's going to swap back and forth as we process this, right? Currently, the infinite digit is 0. But the first time we run this, the infinite digit will become 1 because the entire field will be all hash marks, right? Boy, this is a very tricky problem. I almost feel like I'm misreading it because the problem that I'm talking about, the fact that we flip back and forth, it just doesn't occur in this example, but it definitely does occur in my input because, again, the 0th pixel is a hash mark. Meaning that the 0th pixel doesn't align with what we flood fill this with. Boy, I almost feel like I'm just misreading this, but we can go ahead with this problem. I just want to double check that I'm reading it correctly. I thought this was going to be really easy, and now I've just like this curveball is very interesting. Okay, well, as before, I just opened this input like 5 times. As before, I think what we can do is just start with an easy problem just to sort of get our minds into it. And the easy problem is just writing the parser. I'm going to reload the window really quickly. I just created a new directory. I just want to make sure that the new directory is recognized and we can be on our way. All right, we're going to grab the input, stick it into a local variable. We're going to split it into an iterator over the lines. And then our lookup table, which is going to be a vec of chars, is just going to be equal to the first lines, converted into characters, and plopped right into a vector. Then we are going to consume a new line. And now we're going to read in the input image, right? And the input image, I think what I'm going to do right now is just find the locations of the hash marks, right? And then I should be able to kind of like reverse the polarity of that if I wanted to, but that's what I'm just going to do for now. So what it's going to be is a set of two tuples indexed by row and column, and we're going to just treat the upper left-hand corner as 0, 0 for now. Let's just pick that. So we're going to say our input image, it's really just our current image, right? Which is a hash set of, I don't want usize, usize. I actually want like I64, right? Because these can go negative. I64 is a new hash set. And we are going to iterate over the remaining lines. And let's actually also get the index here. So it's the row and the line in lines.enumerate. And then we're going to iterate over the characters. And we are going to say if the character is equal to the hash sign, then our image, we're going to insert image.add. I don't understand the verbs here. You insert into a hash map, you add to a set. We're going to add the row column tuple here. Oh, and we need to enumerate over these characters, just like we enumerated over the lines. And then I think actually add is not, I think it was insert. I think it was just like I wasn't using the right, I didn't have a hash set imported. Okay, what are you complaining about? Row and column. Oh, they're not I64s. I see. Can I do an as here? I can do an as here when I actually insert. I64, that range fully encompasses usize, so we should be fine there. All right, so why don't we just go ahead and debug print our lookup table. What are you complaining about? Added something I don't need. And let's go ahead and make day 20A. This is our lookup table. Our lookup table is hash, hash, hash. Correct. And it ends in dot, dot, hash, dot. Dot, dot, hash, dot. Okay, so we got that. We got the lookup table correct. Now getting the image is going to be a little bit weird because when we print the when we debug print the image, it's going to be this sort of like unsorted set of row column coordinates. So in order to check that, I think I just want to find the first one that's on. Like, do I see in my output here 0, 0, 0, 1, and 0, 2? And that's going to be hard to do because these are on multiple lines. Well, let's just see if I can look for 0, comma. Oh, this can be tricky. What if I do space 0, comma? I could always sort these, but yeah, this debug print's not going to help me out in terms of like just verifying that I got it right. I'm not super concerned about it though. This feels like a relatively simplistic thing that we're doing here. Okay, so that being said, now we actually have to try to run our algorithm, and I think we're just going to be blocked for a while because like we can't actually run the first step trivially running the first step means that we're going to have an infinite field. Like this image is just going to have like an infinite number of entries in it. So what we really want to know is, for the second step, we need to actually reverse the sense of what the image is. We need to actually store locations where it's not infinite, right? And so let's actually try to map that out. And I think here we can use the example input here. So I'm going to go ahead and copy this down here. And what's going to happen is all of these dots here are going to become hash marks. And I just want to replace in my selection. Is that possible in VS Code? I think I do this. Yeah. So I'm going bit by bit here. Why are you fighting me here? I wish I understood my editor a little bit more. This definitely wouldn't be an issue in Sublime Text. VI, I could probably do this a little bit more easily, but for some reason I am making a selection, right? I am selecting this line. Seems pretty clear. And it's saying there's no results for dot when there clearly is a dot. There's nothing else but dots inside the input. And I was able to successfully do it this first time around. But anyways, we're going to have dots here. And then I'm not sure about these lines. I'm going to indent all the lines I'm not sure about. And these will all be hashes, right? Like I said before, the kernel that's going to actually matter is this one here. Which means that everything in here, in this selection, let's go back one, those are all going to be hashes. Similarly, all the way down here. And then these are also all going to be hashes. And then there's an open question about what this is going to turn into, what this is going to turn into, and what this is going to turn into. Right? And we basically just need to calculate that. So what we're saying is if we're on an odd, if we're trying to process, okay, we're on step 0. So I guess how we enumerate these steps matters. I want to say this is the first step. Okay, this is step number 1. If we're on an odd step, then we actually know that most of the background is going to be going from hashes to dots. And what we will still need to concern ourselves with is the upper leftmost hash and the lower rightmost hash. Is that right? Actually, what we need to know is all the extrema on both dimensions. We need the lowest column that has a hash. We need the highest column that has a hash. We need the lowest row that has a hash, and the highest row that has a hash. And then from there, we can basically determine what is going to be there. So what we're going to do is we're just going to do the regular image processing in this area. Okay? So let's try that as our first step. And we'll probably end up just putting in a loop, right? So let's go ahead and say, so the question is, do we want to iterate over everything here, or do we want to keep track of the lowest and highest? I think we want to keep track of the lowest and highest. Let row min equals I64 max. Let row max equals I64 min. Let call min. So we're going to have a call min and a call max and a row min and a row max. Okay, so once we see a hash, we're going to say if the row min, we'll say the row min is equal to row min dot minimum of the current row. I think I need to pass it by reference. Oh, and it needs to be an I64. Oh, and these all need to be mutable. Gosh, there's so many things I'm doing wrong here. Okay, and then the row max is going to be the maximum. And because I initialized row max to the minimum possible I64, the first time we run this, this is always going to get written over. And we can do the same thing with columns. Okay, so now that we know that, what we care about is starting a loop. We care about starting a loop that where I think it's one less than row minimum and one less than column minimum. Which in this case, in this particular example, is going to be we're gonna care about this pixel here, right? So for row in row min -1 all the way to row max +1, and then for column in call minimum -1 all the way to column maximum +1 inclusive. We are trying to figure out what the value for the next step is going to be. And so what we're going to do is we are going to say, and let's actually create a second hash set for the next image. And we're going to see how to relate it to the previous image. Okay, so what we're going to do is now we're going to just do this iteration for row and column. We're going to go for I. We're going to accumulate a binary number, right? And we're going to basically, it's going to be a vector of characters. And this is going to be digits. In fact, I wonder if this should be zeros and ones, but you know what? I think it's okay for now. So for I goes from row -1 to row +1, and it's inclusive of that next row. And j goes from column -1 to and including col +1. And now we're just pushing characters on to this digits array or digits vector. Push. We're going to say if, or we can, yeah, let's do next digits.push if the previous image, right, contains ij. That means the previous image has, if it has a hash there, then we are pushing a 1. Otherwise, we are pushing a 0. All right, I don't love the look of this expression. So what I'm going to do instead is I'm going to put digits.push1 in here and digits.push 0 in the else clause. All right, so it's actually the character 1 and the character 0. And the reason why we're pushing characters is what we're going to do is convert this into a string once we're done iterating over these. We're going to collect these into a string. It's a capital S string. And then we're going to parse. How do I parse binary again? I believe it's I64 from string radix. The radix is 2. And the source string here is this. But why not instead? Why don't I just call this let s binster is equal to this thing. And rather than use a turbo fish here, I'm going to use a type annotation, which looks a little bit cleaner to my eye. I don't know what's idiomatic, but... And this is the index into the lookup table. And let's unwrap it because we know it's binary. And then, so the eventual character, the pixel is equal to, we're going to look up in our lookup table what the index is. And that's it. That's the character, right? Oh, and this is actually an I64, right? Oh, sorry, U size. Yeah, it's a nine digits, right? This is doing an iteration over a 3x3, 3 columns, 3 rows. That's 9 total digits, and a 9 digit at most can be 512 bits. So we're looking it up here, and this is our pixel. And what we're going to do is we're going to say that our next image dot insert. We're going to insert if the pixel is equal to a hash. If this value in the lookup table is equal to the hash, we're going to add to our next image set. Now, as I said before, this isn't going to be complete at all. And I'll tell you why in a second. The row and column is going to be row call here. Yeah. I may even want to specify and call this like input row, input, or output row, output column. Out row. Let's put an out call. I almost want to put underscores there just because out is really hard to parse out. Really hard to read. And let's call Roman rmin. I think that is easy enough to understand. Rmax, Cmin, and Cmax. Okay. So the issue with this after our first iteration is that this next image is not actually complete because, like I said before, the next time around, everything outside is going to be a hash mark. And if we try to just run this naively going to the next time, our row min and row max would just need to be negative infinity and positive infinity, and the same thing for call min and call max, right? Now, since we know that they flip, there might be a way where we can say, well, the next time we run this, we're gonna actually switch into tracking the off pixels instead, right? So we can say next image, rather than keeping track of what the on pixels are, let's keep track of the off pixels. Okay, so if this is an off pixel, if it's an off pixel, then we insert into the next image, right? But we need to know whether we're in the, like, we're processing an odd step or an even step. Or rather, let's call it an even step. Let's call this step 0. Because what this will be is a loop, or a for loop, and we're going to run it twice, right? For step in 0 to 2. And we need to not modify. I think we can modify rmin and rmax, and they are not going to get reprocessed here. Is that correct? Can I just modify rmin right here? I don't think this is gonna like get reevaluated. I think what happens is this range gets evaluated into an actual range value that is then set by the time you run this iteration. It's not like it's reevaluating this expression every time you loop. That's my understanding. And the reason why that matters is we basically need to know what character we're looking for, right? So if step mod 2 is even, that means that all of the infinite pixels are going to get turned into hashes, right? And so what we really want to keep track of are the input pixels that are dots. So that otherwise, we care if it's a hash here, right? And then also what we're going to do is we're going to do this whole business here. We're going to update the mins and maximums for the next iteration. Row is actually out row. Call is just out out call. And we would actually repeat this same code down here. But I'm now thinking that maybe what we can say is let tracking char, or the char we care about, let's just call it let C, is equal to step 2 is 0, then we're going to actually be tracking dots. Otherwise, if it's, sorry, step 2 is even, we're going to be tracking dots. Otherwise, if it's odd, we're going to be, the next loop, we're going to be tracking hash marks. And so instead, what we can do is the lookup equals the tracking character. then we can add it to the next image. And then what we do is now that once we're done processing all of those, we say that image equals next image. Okay, and then I think we need to do one more thing. Right. If image contains a value, we need to know whether the image is supposed to represent the image, like the set of values inside of our set. Do those represent the ones or do those represent the zeros? And by the time we get to this step, by the time we get to like the top of this loop here, we're basically saying if let image value let inval, we're just going to say by default it equals 1. Let mute inval, let mute inval, and then not inval. How about contains? And what's the opposite of contains in a single word? Exists val and not exists val. Okay, this is the best language I can think of right now. Is this. However, if we are on an odd step, if step mod 2 is equal to 1, then we're going to swap these two. Exist val equals 0, not exist val is equal to 1. Is there a more graceful way we can express this? How about this? Let exists val not exists val is equal to, if step mod 2 is equal to 1, or is equal to 0, then it's just 1 and 0. Otherwise, it's 0 and 1. So here what we're doing is like if this point exists in the image, then we push the exists val on there. Otherwise, we push the not exists val. And that's basically because each time we loop here, what this image is going to represent is opposite. So the first time around, image means image is going to say, I'm going to contain all of the pixels that are hashes. However, we get down here, and then we're basically saying, oh, you know what's going to happen is we're going to end up with an infinite field of hashes. So what we want to actually track the next round is just the stuff that are dots, right? So we're going to, once we override on line 68, the old image with the next image, the old image was tracking all the hashes. This new one's tracking all the dots. We're going to go up to the top of the loop, and then we're going to say, okay, now we're on an odd loop. So that means that the stuff inside the image is actually the stuff that's off, and the stuff that's on in the image is the stuff that's is not included in the image set is actually on or lit, right? And then I think row min and row max actually need to get this is incorrect. There's no trivial relevance between the previous value of r min and the previous value and the new value of r min. So I think what we actually want to do is we want to take this stuff here, this resetting, and for each loop we're going to call this the next, just the same way that we have a next image here. We're also going to have next r min, next r max, next cmin, next cmax, and so on and so forth. And these are all going to be nexts. We're going to prefix next here to all of these. And then now we're going to update rmin is equal to next rmin. And then we're going to do the maxes. And then we're going to do the columns. And then we're going to go to the next step. Okay, so I think that's our algorithm. I'm hoping that this will work. And actually, we're building a lot of assumptions into this code here because we're assuming that the 0th value of the lookup table is a hash, which means it'll flip everything that is infinite from a dot into a hash. And then we're also assuming that the last value, which is the 511th value, is a dot, which means that it'll flip all what were previously hashes. Like if you have a field of 9 hashes, a kernel of 9 hashes, those will all flip to, or at least the center one will flip to a dot. Okay, this one's confusing to talk about. Maybe actually less confusing to talk about than yesterday's problem, but still confusing to talk about. And then what we need to do is, I think we actually want to know what this step value is. The reason why is when we come out of this, we kind of need to know how many are lit, right? Actually, you know what? We don't need to know. It always is going to have to be an even number of steps. We're always going to have to run an even number of steps. And the reason why is that if we run an odd number of steps, if we just run like the first step, the number of pixels that are lit is infinite. Because of the whole complexity of this problem is the fact that they turn infinite. The on pixels become infinite every other step, right? So if I run the first step, or the 0th step rather, I'm going to have an infinite number of on ones. So if I've got an infinite number of on ones, then I'm in trouble. So I just basically need to print the size of image at the very end of this. And this is the number of on bits. Right? Now, what's a little bit frustrating about this particular solution is that I can't actually use the sample input. Again, because the meaning of the infinite pixels changes because of the way the lookup table is structured. Boy, I really wish I didn't make a reading mistake, but this is, I think, what they're trying to convey here. I'm going to go ahead and just run this sucker and see what happens. 5,583. Okay, so we got it right. So I think we did actually read this problem correctly. This is great. Oh, I can't push. For some reason, my VS Code has had a hard time getting my environment variables, including like getting access to the SSH agent. So I haven't been able to push from this terminal, which is fine. You still can't quite make out the details in the image. Maybe you just don't enhance it enough. If you enhance the starting image above 50 times. Hey, CrazyWolf770. You're saying it's interesting how you approach this puzzle. You straight skipped the sample and directly figured out the flip issue and tried this. And also first tried this one. Impressive. Thank you very much for the compliment. I think in this case, I said it earlier while I was trying to solve this puzzle. Basically, as soon as I looked at the input, I realized that we were going to be flipping. And I don't think I would have been able to get anywhere unless I analyzed that problem. Like, it would have been easy for us to just try to implement this algorithm, assuming that we weren't flipping the infinite pixels. But you just wouldn't get anywhere, right? As soon as you got to the processing your input, you would hit your problem would infinite loop, and you would just have to figure out how to deal with that. But yeah, thanks for the kind words. I appreciate it. So the second day, sorry, it's not the second day. The second part of the problem, we're just supposed to run this 50 times. I think we can just crank this number up to 50 and just see what happens. Now it's going to grow, right? Like, I think what they're describing here is sort of this thing that grows. I don't know if it's equivalent to Conway's life. It's really hard to know because it's basically dependent on the encoding of this lookup table here. But what I'm going to do is, like, very laboriously just copy the first part of the problem into the second part of the problem, make a new directory for it, and we'll push ahead once I'm done with that bit of busy work. Okay, gonna reload the IDE real quick. And we're gonna go ahead and open 20v. And let's just crank this number to 50. And we will cross our fingers that it doesn't infinite loop. Ooh, that didn't look like it ran. Okay, now it's taking forever. I wonder if I should at least print something out that indicates which step we're on, just to make sure that we're not looping infinitely. Okay, well, finished. I'm just curious, if I make a release build, will this run any faster? I mean, naturally it will run faster. So it did run quite a bit faster, actually. So if I time that, yeah, it takes like 1.5 seconds. So literally the only change from the first part of the problem going into the second part of the problem is just the number of times you run this. And we got the right answer. That's really nice. I'm pretty happy about that. Boy, I feel like we really kind of lucked out on this one. I spent some time just making sure I read the problem correctly, because I think really the crux of it was just realizing that there's this flip here. And this algorithm only would have worked if the very last element in the lookup table is a dot. If there's no flipping back and forth, you're just basically hosed. And so this is actually kind of interesting, because normally, well, I shouldn't say normally, actually. I don't know why I'm making such a big fuss out of this, because I think the people that design these puzzles, they're really deliberate about choosing input that fits the problem. For example, yesterday's, for day 19, they made sure that there were like 12 beacons that were shared between, like, basically every set had at least 12 beacons shared with at least one other set, right? They had to design the inputs such that, like, you could have that criteria there. Otherwise, you might not have been able to come up with an algorithm to find the overlaps. This one was especially kind of subtle and tricky, though, because, like, if the lookup table wasn't arranged just so, meaning that the first one wasn't a hash and the last one wasn't a dot, like, they basically either need to be both be dots, or they need to be opposites of each other. Crazy Wolf 770, how long did you need for day 19? I really struggle with it. That is a good question. I believe the video for that yesterday was like 2.5 hours or something like that. And so that was me working on it while talking out loud, which I think probably you would think that would slow you down, but actually talking out loud maybe has its benefits as well, because, like, if you say something absurd out loud, it's a little like rubber duck programming, right? Like, when you rubber duck with somebody, you kind of, like, figure out your problems as you say them out loud. So it took me a couple of hours yesterday. I'm trying to remember, I don't think that the second problem was that much harder than the first problem yesterday, right? You just had to, like, track an extra variable. So it probably took me another 15 minutes to just solve the second part. So yeah, it was a solid couple of hours for me working on the problem yesterday. However, I actually spent multiple additional hours on yesterday's problem trying to optimize it, because it takes like 10 seconds to run, right? Like, let me time make day 19b release, right? Let's just run that. So it's building, and now it's just cooking. And it's probably going to come out to be like 12 or 13 seconds here. I don't actually even trust this time command, because it always feels like it takes longer than it actually... Like, this feels like it's taken at least 20 or 30 seconds already, right? Yeah, so that was 22 seconds. I think if I run it again, the compile will be instantaneous. Maybe there'll be something in CPU cache already. But it's pretty freaking slow. And I spent several hours trying to optimize the solution to see if I could make it go faster. And I didn't really come up with a great solution for that. Yeah, mine is 6 seconds. I checked some solutions, and there's a PHP solution in less than a sec, but I couldn't figure out how it worked. Yeah, well, I don't... Like, my solution was basically, like, okay, take a set that you already have resolved, and you know its position relative to the first scanner. Take one of those, arbitrarily pick another set that you don't know anything about, or you haven't found an overlap with yet. For that second set, rotate it using all 24 possible rotations. And then for each one of those rotations, compare it to the current set that you currently have and try to find like the common shape, right? And my way of finding the common shape was basically to say, okay, for each one of those sets, let's pick one of the beacons in each set as the arbitrary origin, right? And then what that means is we're going to take the origin's position and subtract that position from all the other beacons in that same set. And we're going to do that the same thing with the second set. And then we're basically going to do like a basic, a set overlap comparison between those two. And if you have more than 12 in the overlap, that means you've found kind of both the orientation and offset of that second set that will allow you to resolve it to the scanner zero's space. And all of that math that I was doing to kind of like convert origin spaces just took forever. And also doing all the rotations. I came up with a solution that does like pre-compute the rotations at least, so I'm not redoing that every single time, but it's still like freaking slow. And my suspicion is that people who can solve this problem like essentially immediately, and I kind of think that all advent of code problems, or most advent of code problems, have solutions that will run in an interpreted garbage collected language in like less than a couple seconds. I haven't seen too many other problems that require just like extended runtime. My suspicion is that there's just structurally a different way of attacking that problem than what I did. I think there were some people that were basically just like, they were calculating Manhattan distances and seeing just like how many, and I didn't really know how to do that because I just like, Manhattan distance is relative to something, right? So relative to what? Maybe there's just like some way you can find the center of gravity of a particular beacon set, right? You can say like, okay, let me average all of the XYZ offsets. And maybe if you do that, there's some way of doing the comparison. I just didn't know how to figure it out in a way that felt general. So yeah, like long story short, I came up with a solution, but these things don't run very quickly. In fact, I think at the beginning of this stream, I said, well, if I have some extra time, I'm going to try to optimize my day 19 solution. But honestly, I am a little bit out of gas mentally, so I think maybe that will have to happen at some other time. So yeah, that was day 20 for Advent of Code 2021. Really looking forward to the remaining 4 or 5 problems. Crazy Wolf, thanks for jumping into the chat and chatting with me. It's been fun. We'll see everybody tomorrow.